the average copper on the type 2 side, then for very strong coupling we have pure repulsive potential. But if we have a weak interdependent coupling, then we see this very nice minimum exactly corresponding to the vortex much
whatever the coupling,
we always have this minimum. Basically there is a broad space of interdependent coupling where this type 1 is but remarkably, if you tune this average parameter in two bands,
so I'm
exactly 1 divided by stating that then whatever the coupling, you always have this type 1 corresponding to 5. Then this type 1.5 regime is extremely stable. You have only that.
diagram which separates the conventional.
So I'm concluding my talk by stating that in two-component superconductors, a very nice regime of type 1.5 conductivity can be realized, and it generates the area of the HT diagram which separates the conventional mixed state from classical Meissner state, and here you have vortex clusters,
Magnetization as a function
stripes. And these states have a lot of similarities with the situation around exactly this point copper 1 divided by square root. So if you analyze local images, then we have already reasons to suspect that magnetization as a function of 1.5 magnetization and local magnetization shows
like a layer by type 1 and type 2 is not similar to this
conclusions. Type 1 superconductors so far have found this.
So the combination of the vortex repulsion and interaction in the same material leads to the appearance of novel vortex patterns, exotic vortex arrays, vortex clusters, vortex stripes. These patterns we have directly visualized by using detail decoration and speed microscopy, and we did some analytical modeling, but also large-scale molecular dynamics calculations, and they are in good agreement with our experimental observations. Finally, the last slide is, it was shown already yesterday, that basically we hope that, especially along these iron pnictides, new superconductors, there are certainly two band materials, but we don't know yet which of them could be classified as type 1.5 superconductors. With that, I would like to stop here and to thank all of you for your attention. Thank you very much.
Thank you. Questions, please.
The phase diagram that you showed, your schematic one of the type 1.5. Exactly. There you go. That's a beautiful picture, but the data you're showing from MGB2, what you call high field is half an Oersted or 5 Oersted. I think one of your plots showed that
higher.
Well, I think your 1.5 region in MGB2, could you show us a phase diagram for MGB2 that delineates where your 1.5 is?
No, this phase diagram I don't have. I have only vortex distance.
Right, but
that one.
At low temperatures, at what field does the 1.5 exist?
Just like this one. So our yeah. So this is 15 Gauss.
Yes, but that's an incredibly narrow little sliver.
Yes.
So you're showing the 1.5 over 25% of the phase diagram. I think it exists over orders of magnitude less.
So I'm not that pessimistic, Paul. So what my main idea is, I agree with your point. There is no reason to argue here that basically in our experiments we did not explore all areas here, not at all.
Right, but it's a tiny little spot.
It's not tiny. No. If you go to the field range here, if it's tiny for you, it's a matter of taste. Yeah, so we go from this field to that field, but we claim that our data are different from this expected curve point.
What temperature?
I didn't say, so in this case it's 4.2. I didn't say that we explored the full phase diagram. Never. Not even once in my talk. And the picture was schematic.
Above 0.5 millitesla, it's
Yes.
the same as type 2.
Exactly. Yeah, now I see your point. Okay.
Yeah.
Now I see your point. Because these curves can merge as well. I agree with you.
Okay.
Yeah.
So it's a very small region in bare space.
So you see, there is evolution in your objection already. First you call it time, now you're going to walk.
I want to make 2 comments. First, that clustering integration experiments
Yes.
is very common in many superconductors, but definitely type 2. And I'd like to draw your attention to the beautiful talk which will be given in about half an hour by Kenna Kaliski from Stanford Group. And she shows actually a lot more extreme picture of this clustering in an extreme type 2 superconductor. It's 1 to 2 ferronuclides, so people run out parameter of about 100. So definitely clustering may not necessarily imply 1.5 superconductivity. The second point is that the numbers you're using for concluding type 1 half superconductivity actually they're very unconventional for the penetration depths in particular. Penetration depth is about from 80 to 100 nanometers.
So penetration depth,
The global penetration depth. Partial penetration depth don't make any physical sense because when you calculate a vortex, 2 bands are phase locked, so you only need to know the physical scale on which the field decays. So it's about 100 nanometers. Penetration depth in the pi band was measured by STM by Eskelson. It's about 50 nanometers.
it's an agreement. We took their data.
Right. So if I take the ratio, I get the Ginzburg parameter for pi band about 2. So it's marginal type 2 superconductor. So if I plug it in Ginzburg-Landau, as Babayev did in his recent preprint, in which he for the first time take into account the interband coupling, it's not published yet, but it's online. The fact that the critical temperatures in the sequent pi band differ by a factor of 2, at least, tells me that in the region where we can apply Ginzburg-Landau, type 1 cap doesn't exist, and that follows from his calculation.
So as far as I'm concerned, I found 3 points, actually, not 2. First is that we are saying that vortex clustering, nothing can happen. And that's why, actually, when we observed vortex clustering, then we applied different magnetic fields to explore quite broad range, contrary to what Paul was doing. And then, systematically, what we have found is this. So instead of having a homogeneous vortex pattern, vortices prefer to cluster. And we are sure that this is just what's going on. Then, you can, knowing positional vortices, you can, of course, derive from the analysis vortex-vortex distance, and then you can plot it, and then you see a drastic difference with this behavior, which, by the way, we also have confirmed on our reference laboratory all the time. There was no problem with that. There was some sporadic clustering, but not that pronounced. Also, we have recently studied with the scanning hole probe microscopy nuclides, where we do see clustering, and we hope to see type 1.5, but no, we have found only one distribution and not bimodal. And with that, I agree with your comment that in iron arsenic nuclides, it's not yet established at all. So now about...
You can see dimers very clearly.
Okay, no problem. We also saw dimers, but when you try to draw bigger clusters like that, we did it on these nuclides, and we hoped to see another type 1.5, but we didn't detect that. Then your remark about lambda. So of course lambda, from the point of view of electrodynamics, is 1 divided lambda 1 squared plus 1 divided lambda 2 squared. We know that very well. But we also know that lambda changes dramatically, as you know as well, if you change the impurity concentration. And very quickly, if you get crystals which are less clear, we do not see this clustering, these patterns, and what we have called type 1.5. It simply disappears. Now about this Ginzburg-Landau type treatment, that's why we did this analysis. I agree with you about comment on this Babayev paper, but what is shown here is truly remarkable. That basically, you have to deal with this one, with the denormalized, which is in line exactly with your comment. And the big question is, do we have something different from type 1, which is this curve, and type 2, which is this curve? And my statement is yes, we do have something with this minimum. And this minimum is responsible for driving forces much closer to each other and to form the clusters. And we couldn't kill this one unless we take a very, very strong interband coupling. Correct. If I take very strong interband coupling, I have exactly what we have had already for 60 years, like this one, and that this is typical for type 1 and type 2. But there is a lot of space to have also this and that. You can interpret anyway, and it's up to you.
Victor, since you mentioned me, I have to make the following statement. My comment was misunderstood, unfortunately, by most people, because I cannot write a comment and say a Fitzroy letter is not good or make negative statement. So I just wrote first the old history, which apparently was not known by the authors of this paper. 40 years ago, a lot of work was done experimentally and theoretically, and it was nice. But I just wrote, it's very interesting, but it requires further investigation. And this encouraged many people who wanted to write a comment. So I have to excuse for this. Now, my statement is, type 1 and type 2 superconductor, these names make sense only within Ginzburg-Landau theory. Simple one-component Ginzburg-Landau theory. If you have a different material, like niobium or thorium nitride or was also observed in indium and thallium 40 years ago. Phase diagrams were published, for instance, experimentally by Auer and Ullmeyer for kappa and temperature, and the material changed character from type 2 to type 1 to type 2. So materials do not have the character type 1, type 2, but a material at a certain temperature, but it can be described by Ginzburg-Landau theory. But if you have a different theory, like two components, then you may define, but if everybody can have a different definition, and the definition does not change physics at all, and the physics is that there can be only one lambda. Lambda is an electrodynamic quantity, which is just given by a derivative of the free energy with respect to vector potential. So whether you have one component or two or three components doesn't matter. There is one lambda. And the picture where there was a so-called type 1.5 superconductor with a vortex with two magnetic fields. This is, of course, there is one magnetic field. And when one solves, as was shown now in a recent paper, which is in condensed matter by Babaev he took into account the coupling between the vortices. The paper, which is always quoted, said there are two independent bands, and the coupling term we disregard. Then you should have two critical temperatures. And it's a fact that in magnesium diboride you have one critical temperature. This means the autoparameters will be either proportional to each other, they are coupled. And you cannot have two independent behaviors. And I would not call it one band this time, one band this time. You can call it 1.5, 1.6, 1.7, whatever you want. But this doesn't change the underlying physics. And in the last 2 months, I worked very hard together with a theorist in Mukunda Das in Canberra, and I'll have a talk on Thursday morning where we do this in detail. And I also remind of these old papers. When I was a thesis student and the 6 years after this, all my colleagues worked on vortex attraction. So this was a very topical field. And they were experimentalists, for instance, and they published this phase diagram of pendulum. So again, the kappa maybe between 4.6 and 1.5, and you find attraction. The vortex clustering is common.
That's exactly our point. If we define it in terms of vortex-vortex interaction, then in this, what we call type 1.5, you have additionally this. You will never reproduce it in this. That's clear.
I believe that we have to close the section because
we take, sorry, just a moment. We have to take again the speaker.